All right, to reiterate some of the things we talked about yesterday, one of the things that we really focused on was the word Zeph. What does Zeph stand for? Effective nuclear charge. All right, what Zeph is the ability of the nucleus to have an attraction on valence electrons. All right, so let's re-say that and let's break it down. The ability of the nucleus. Why are we worried about the nucleus? It holds everything together. The ability of the nucleus to have an attraction. What does an attraction mean? You can define it any way you want to have it. But why is there an attraction? Perfect. The nucleus is positive and the electrons are negative. So there's a charge attraction there. Now, it's the ability of the nucleus to have an attraction to the valence electrons. Now, why did I not just say electrons? Why did I say valence electrons? Okay, where are the valence? Outer shell. Do you think the valence shell is going to determine the size of the atom? Yes, that's what this is all about. So we talked about Zeph. The stronger the Zeph, the blank the size of the atom. Smaller the atom. The lower the Zeph, the blank the atom. The bigger, the larger. As we move left to right, what happened to the size? It got smaller, so what had to happen to your Zeph? Had to go up. What happened to the size as we went down? It got larger, so the Zeph had to go down. Now, there was one additional reason why Zeph went up as we go down, Zeph goes down, so it gets bigger. What was one of the additional reasons why Zeph went down as we went down? What are you adding every time you go down a period? More electrons, so you're adding more orbitals. Very good. So let's kind of keep that in mind. So, atomic radii. Let's talk about what the atomic radii is. We're going to talk about three trends today. We're going to talk about atomic radii, ionic radii, and valence electrons. Valence electrons is the easiest. The boundaries of an atom. Let's pause right there. What does it mean by the boundary? The end of it, right? How far it ends. Okay, that's the boundary. The boundaries of atoms are fuzzy. Why are they fuzzy? Okay, I mean, there's a lot of good answers there. If this is the nucleus, the electrons, they'll eventually catch up, are out there somewhere. We don't know where they are, but they are somewhere out there in that general vicinity. And the problem is we can't put a point on it and say this is where it ends. So how do we determine how large an atom is? Do it again. What is that? We're going to take two atoms, and what are we going to do? Slam them into each other. And once we put them together, how can we then determine how large it is? Measure the distance from where? The nuclei, and then do what? Cut it in half. Yes, sir. I mean, how do you make a baseball beat a bat? It's a particle collider. I mean, that is a question that's so far up here that only those really smart people can answer, like those nuclear physicist people that work underground in labs and don't see the light of day. I like the beach. I mean, I don't really care to know how they do it, to be honest with you, but they do it. So compare the different atomic radii. They must measured under specific conditions, and this is what it is. The atomic radius may be defined as 1/2 the distance between the nuclei of identical bonded atoms. You know what I forgot to do? No, it's recording. Now, again, radius, half the distance of two atoms that are identical that are bonded together. So if you look at this picture, let's look at the top right-hand corner. Do you agree that those are two bromine atoms that are bonded together? Yes. Bromine is that thing we just talked about. What is that? Bromine is a diatomic. Alright, so, again, we know that atoms are not perfectly spherical objects, so sometimes we just have to draw them that way to see if they make sense. But again, when you take this, we know where the nucleus of these things are, and so you can take the distance and divide it by 2. So again, atomic radius is half the distance between the two nuclei of a molecule. That's the definition. Now, do you agree that if I showed a 4-year-old that picture, they could tell me what's going on? As I go left to right, what's happening? It's getting smaller. As I go from top to bottom, it's getting... You're not 4 years old. That's not what I want you to know. Yes, it is important that you understand the trend, but it's that you understand why it trends that way. So on the test, you may see 1 or 2 of several questions. What is the trend? But more than likely, you're probably going to see what? Why does it trend that way? What causes this trend to happen? I'm going to say it gets smaller because ... and you're going to have to understand the trend. So let's talk about why it gets smaller. Atomic radii actually decreases across a row. And then when it says due to, do you agree that that is going to be your why? Here is the thing you need to learn. Now, there are going to be 6 trend topics that we're going to talk about. Probably Tuesday or Wednesday of next week, you're going to get one sheet of paper. It's going to have all 6 on it. We're going to break them down on that one sheet of paper. That's going to be what you're going to use to study. You can use the notes too, but it gets all of this and it puts it on one sheet. So it's going to be a lot easier to look at. So, due to an increase in the effective nuclear charge. What is nuclear charge again? ZEF. So your ZEF is increasing. And here's why. If I were standing in between you and the door, what would I be doing? Shielding. That's the key word there. So, when we look at the lithium atom, it's got 3 protons sitting here in the center. It's got 2 electrons on the first level, and it's got 1 valence, or 2 valence, or 3. 1. Why? It's in group 1. So what are these 2 core electrons doing to that 1? They're shielding those 3. So essentially you're going to neutralize it to just 1. So you've got 1 electron to reach out there and grab that thing. Okay, that's an issue. Well, let's go over and let's do neon. We've got 10 protons in the center. We've got electron here, and then how many does neon have? It's got 8. I should not have drawn that a different size. That's actually, let's erase this and let's draw it the same size. So we've got 8 electrons. So now you had 1 pulling on 1. Do you agree that there is a strength of attraction there? Yes. But here, what do you have pulling? Well, we got to cancel off 2 of them, right? For those 2. So now what do you have pulling? 8 on 8. What's going to pull stronger, 1 on 1 or 8 on 8? Do you agree that 8 things can pull a lot harder than 1? So what's going to happen to the size of this thing? It's going to get smaller. So that is why it's going to get smaller. The ZEF, the effectiveness of the nucleus must go up. That's why it's going to get smaller. Does that make sense? Stop me if it doesn't. Nucleus. Exactly. Okay? All right. Now, within each group, now I'm talking about, when I say within each group, I'm talking about this thing. Okay? Within that group, what do you notice happens to those spheres? They get larger. Within each vertical column, the atomic radius tends to do what? Increase. That's obvious. You can look at the picture and tell within the period number. There's 2 reasons. I'm actually going to go to the next slide so you don't have to cram it in on that. I want you to, it's actually 2 slides down. Let's find this one. It's just 2 down. Atoms tend to be larger the farther down the group they are found because an increasing size of the electron cloud. Now, what is a better way to say electron cloud? Very good. You have more orbitals. So really, we're adding more orbitals. Okay? So not only does the more orbitals increase, as the number of suborbitals increases, what also happens? Because you have more orbitals, ZEF must go down. So add that little bullet in there as well. Your ZEF must go down. So let me draw you a little bitty picture. lithium. Alright, so we've got 3 protons. We've got 2, 2. Do you agree that that's lithium? Okay, let's go down. Let's go to sodium. So we've got 11 protons. We've got 1 there, there. How many would the next ring hold? 8. Very good. So I've got 8. And then what would the next one have? Do you agree they both still have 1 valence electron? But has it gotten larger? Why did it get larger? You've added what? You've added another orbital. Well, let's even go down farther. Let's go to potassium. So we've got 19 electrons. We've got 2. We've got 8. And we've got 8. And then we've got 1 electron again. Obviously, is it getting larger? It has to get larger because you have more orbitals. You have more electrons. Can 19 fit in the same space 3 can fit in? No, not at all. So that's our issue. That's our cause and effect there. That's not what I wanted to do. Say that again. Yes. Okay. Go back up 1 slide to this one because we skipped it. And again, it's restating what we've already said. Atoms tend to be smaller the farther right we get. So, what I mean here is as we go from group 1 to group 18, they're going to get smaller. Why? Increasing positive charge of the nucleus. Do you agree we have more protons? Okay. Which attracts electrons towards the nucleus. Basically, that is the definition of Zeph. So your Zeph must go up. Your Zeph must go up. Alright, so that's atomic radii. I do want you to do this. And I know it's going to be hard to do that, but we did it earlier, so I mean, y'all can fit it in there. Alright, so as you move left to right, your Zeph's going to go up. And as you go down, your Zeph's going to go down, and you're going to increase your number of orbitals. So again, I can show a 4-year-old this picture, and they would obviously know that it's going to get a little bit smaller. Okay? Any questions there? What's up? What's wrong? What's wrong? Okay. Okay, alright, go ahead. It's larger, yes. Now, let's move on to the next one. This is something that is going to be new. There are several things that are important about this slide. Here's a new word that you're going to need to add to your chemistry vocabulary. Do not say that word. That is a chemistry profane word. It is a cation. Now, here's a way to know that a positive ion is called a cation. When you write the positive symbol, what does it look like? It looks like a plus sign. What letter looks like a plus sign? A T. What's in the middle of cation? A T. That's always going to be your plus. It's going to be your cation. Now, let's talk about how you become a cation. How do you become positive? What do you have to do? You have to lose an electron. Okay? You have to lose an electron. Now, here's another fact you need to memorize. This would make sense. When you lose weight, what happens to your size? You get smaller. So if you lose an electron, what should happen to your size? So you decrease an atomic radius. Does that make sense? Okay? Now, the last thing you need to know is, what are those things that turn into cations? Metals. If you don't hear anything else, please hear that today. So what I'm referring to is your group 1 and 2. Group 1 and 2, and this is going to be weird, and aluminum, and your transition metals. Now, why did I pull aluminum out individually? Say that again? It is on the stair step, but is it in group 1 or 2? Is it a transition metal? No, but it is a metal. Okay, and it is going to act like this. So aluminum is kind of that little oddball stuck in the corner, all by itself. So all of these things are going to become cations. Again, how do you become a cation? You have to lose an electron. These are the groups that want to lose those electrons. The electron cloud becomes smaller, so the remaining electrons are drawn closer to the nucleus by its unbalanced positive charge. So, let's look at a drawing. I'm going to take that same lithium that I always draw, and I'm going to put 3 protons in the center, and I've got an electron here, and I've got an electron here. If we want to become a cation, what are we going to have to do? So which one are we going to lose? The one on the outer shell, right? You think that thing's going to disappear? Well, so now, what do we have going on? We've got 3 protons pulling on 2 electrons. Who wins? Where are the protons? In the middle. So if you're playing tug of war, where does that rope go? It goes to the middle. So what's going to happen to the size of this thing? It's got to shrink. Okay, it's got to get smaller. That has to make sense. Okay, so when you lose that orbital, it's got to become a little bit smaller. And it happens with all of the cations. Now, the other word, and don't you dare say it, I know what you're going to want to say. This is an anion. Don't you say anion. That's a profane word. It's kind of like, what does a fish say when it runs into a wall? Damn. What does a fish say when it runs into a wall? Damn. It's not a cuss word. It's an actual wall. This is an anion. It's, don't say, you say it the right way. What are you talking about? It's semantics. It has nothing to do with the real world. Yes. Okay. Let me give you an easy way to remember this. A negative ion is known as a negative ion. An anion. No, I was going to say that. Clearly I know that. Clearly I know that. A negative ion is known as a negative ion, an anion. That's why it's called that. So, if you gain weight, what must happen to your size? You got to get bigger. How do you become negatively charged? You have to gain by the addition of an electron, which increases your size. And the most important thing is, what are those things that turn into anions? Hello? Non-metals. So metals like to become cations, and non-metals love to become anions. That's a fact you need to remember. All right, Allison. All right, so let's talk about trends. Cationic and anionic radii decrease across the period. Here's the best news. The trends for both of them, for atomic and ionic radii trends are the same. So is the reasoning. So if you see anything about a radii, the trend's going to be the same. It decreases across a period. The reason why? The electron cloud shrinks due to the increasing nuclear charge. What is a different way to say nuclear charge? Zeph. Zeph. Okay? The outer electrons in both cations and anions are in higher energy levels as one reads down a group. There is a gradual increase of ionic radii down. The exact same thing. You're adding atomic orbitals, so it must be larger. Now, this is a good picture. No, excuse me, we're going to get in a second. Read this picture up here on the board. Lithium. Does the size go up or down when losing an electron to form a cation? It's got to get what? Smaller. So, did it get smaller? Yes. The thing I want you to notice is look at your sizes. What is PM? Picometer, very good. It went from 152 picometers to 78 picometers. You agree? Yes, ma'am. Exactly. And if it lost 2, it would actually get smaller. No, it did lose 1. Okay, like if we talk about beryllium, beryllium's got 2. If it just lost 1, it would still get a little smaller. Because, here's why. All right, that's a good question. Let's talk about beryllium. Beryllium's got 4 protons, right? Okay, so if it's got 2 on the first shell, come on. If it's got 2 on the first shell, and if it's got 2 on the second shell, all right, I want you to think about this. Do you agree? For this shielding effect, the 2 on the core are going to take care of 2 of them, so you only have 2 left. Well, if you get rid of 1, now you have 2 on 1. So that 2 is going to win. It's going to pull it just a tad bit closer. Does that make sense? Okay. All right, but that is a really good question. So again, the cations get a little bit smaller because they're going to lose electrons. So again, cations smaller, the electron-proton attraction goes up, so the size must decrease. Again, what is another way to say electron-proton attraction? Zeph. Another way to say it. Positive and negative ions form when electrons are transferred. This is the exact same problem, except we're dealing with a larger molecule now, larger atom. Sodium has 11 protons, 11 electrons. It's got 1 valence. What is it going to want to do with that 1 valence? Get rid of it. So notice what happens. You lose 1, what happens to the size? It got a lot smaller. Okay, now let's look at the opposite. What did fluorine do when it gained an electron? It got bigger. It went from 64 to 136. It had to go up just a little bit. Yes? She's on her way. She's on her way. Yep. Okay, so again, anions get a little bit bigger. The electron-proton goes down, and the size must increase. Now let's talk about why it goes down. Guys, let's look for just a second. If we had a tug of war versus 9 on 9, who's going to win? Nobody. It's just going to be a balance of charge. However, when you gain an electron, now who's going to win? 10. The electrons. Where are the electrons? In the center or on the outside? It's going to be on the outside. So it's going to be able to stretch just a little bit more than normal because the 9 can't keep a hold of it. So let's pretend that I send you out on the playground with 9 kindergartners, and you're doing a great job. You're watching them. You're paying attention to them. There's nothing going wrong. But then little Johnny comes out the door. And you got to keep up with little number 10, little Johnny. He is going to do his absolute best to get away from you and climb over that fence and run home. So that's what's happening. That model is going to stretch just a grunt because the distance that he's going to get from you is going to be a little bit harder. It's going to be a little bit more difficult for you to ring in that last electron because you don't have enough eyes to watch all of them. Both. Kindergartner electrons are just alike. They're chaotic, they're crazy, they run 100 miles an hour, and they don't know when to stop. We don't know how to stop them either. Absolute zero. They don't understand that. What? It was good. I mean, it's fact. Okay. Same concept here. Notice what happened to chlorine. What happened to it? Why did it get bigger? Because the kindergartner's just running around like craziness, right? See, sometimes if I talked all chemistry all the time, y'all would be asleep. You'd be drooling out of the left side of your mouth. You've got to keep it interesting, and that's my goal. Okay. All right, I do want you to do me a favor. In this picture, draw a line in between the pink and the blue orbs, and these are going to be the cations. Don't you say that. And these are going to be the anions. Why not just write I? Okay, so we have cations and anions. If you walk into a college class and say both of those words, they may be liable to kick you out of the class. So, yeah, that pisses college professors off, so let's not go there. No, but we've had discussions. Basically, you sound illiterate, and you sound incompetent, and you sound like a lack of a person they need to be anywhere near. You are inferior to their intelligence. You are a waste. You are a mouth breather. Get out. Yo, yeah. I have seen professors kick people out of class because they won't pronounce things right. I'm not kidding. I should. Okay? So notice what's happening. The gray orbs are their size when they're normal. Okay? When it's just the regular old neutral self. The colored orbs are when they have become ions, when they're changing. So notice the purple side. What is happening from the gray, from the gray to the pink? What happens to the orb? It gets smaller. Why is it getting smaller on the atomic level? It's losing an electron. Notice how it's losing it. So let's talk about that. So all of these are your ions. So if we're talking about this pink column, they're all charged ions. So in this first column, how many did they lose? One. They got a little bit smaller. But notice as we go over, they're getting smaller and smaller and smaller because they're losing more and more and more electrons. Notice the difference in boron. It dropped a lot. But when you move to the anion side, from the gray to the blue, what happened to the size? Why? It gained electrons. So it has to increase in size when you gain that electron. Cations? Yes. Okay. That's a good question. Remember how we talked about this. If you have room up there at the top, on the pink side, write metals, and on the blue side, write non-metals. Yes. Anytime you see the pink ones, all of these are metals. Well, what is all of group 1? Those are metals. Those are alkali metals. What is all of group 2? Those are alkaline earth. And then I included the aluminum group or the boron group as well. So all of those fall into that category. Now, we're going to get to this later on, but transition. What does the word transition mean? To change. What is the charge of all group 1s? 1 positive. All of group 2 is 2 positive. All of group 3 is 3 positive. Why are they called the transition metals? They can change. They can have multiple charges. They can be different. If you'll go back to the very last box that we have not quizzed you on yet, which we're going to do soon, on the transition metals, if you look at it, copper can be a 1 plus or a 2 plus. Iron can be a 2 plus or a 3 plus. Lead and tin can be a 2 plus or a 4 plus. It can change depending upon who it's with and who it's around. That's why they're called transition metals, because they have different states of charges they can have. Okay, we're almost finished. The one thing I want you to notice is, let's look at this. The first thing that I have highlighted, do you agree that's just a plain old regular sodium atom? Do you agree that that would be its electron configuration? The second thing I have highlighted is the sodium ion. What do you notice changed from its original state to its charged state? It lost that 3s1 electron. Well, as soon as it lost that electron, who did it turn into? Neon. They all want to be noble gases. But here's the issue. Can it just be running around and say, I'm tired of you, and just drop it like a bad habit? No, it's got to give it to somewhere, so let's think about that. All right, so the chlorine neutral is going to be 3s2, 3p5, and then notice the chlorine ion. How did it change? It went from 5 to 6. So what do you think happens with these two things? Watch what happens. You've got this 1, and notice where it gives it. It gives it to the chlorine. So, can the chlorine just say, all right, thanks, sodium, see ya? No, what do? They make a bond. So, a chemical bond is more or less kind of like a marriage. Okay? Sometimes when they're bonded together, it's you give all and you take all. Okay? Basically, you have to kind of give up your freedoms, and the wife takes all of your freedoms. It's a joke, I'm kidding. Okay? So that's kind of one bond type. Then you've got some other bond types that you share mutual things. Men, you will share in cleaning the household duties. You better learn. Okay? You better learn. So those are the ways you can think about how the electrons are shared back and forth. Sometimes it's a give and take. In this case, it is a give and take. The reason why? Does sodium want it anymore? Nope, but chlorine is begging for it. So it's a give and take. We're going to get into situations where it's going to be well, you can kind of have it, but I kind of want it back sometimes too. And we'll get into what all those things are. So here's what I want you to do. You don't see the green on this slide, right? You're missing the green? Okay, I want you to, base off of the charge on those ions, determine what their new electron configuration would be. So basically, you're going to fill in the new electron configuration based on the charge of those ions, and then write which noble gas it looks like. Everybody good? What do you notice? They're all the same. Who do they all turn into? Neon. Very good. So notice what happens. Nitrogen wants to gain 3, so it goes from 2p3 to 2p6. Oxygen wants to gain 2, it goes from 2p4 to 2p6. And fluorine gains 1, it goes from 2p5 to 2p6. Now, I'm just going to throw this up there real quick. This is the last one. Now, sodium, these are a little bit more difficult because you've got to kind of know what to do with them. But sodium, did it gain or lose 1? Why did it lose 1? It's positive. So when it loses that 3s1, it turns back into 2p6. Magnesium lost 2, so it loses 3s2 down to 2p6. And this is the weird one. Aluminum lost 3. Notice what it lost. What 2 parts did it lose? 3s2 and 3p1. It had to lose all 3 of those, so it completely drops that last orbital. Okay, matter of fact, I think we're almost finished. The last thing is I've got 5 minutes before y'all go to lunch. Valence electrons. This is the easiest, and we'll stop there.